Superconductor levitation. The interesting fact about the superconductors is that the magnetic field cannot penetrate the superconductors. Superconductor deters the magnetic flux, so there is a repelling force between the permanent magnet and the superconductor. In strong magnetic field, the superconductor can even levitate. In this example, I'm going to calculate the interaction force between the superconductor and the permanent magnet, and to demonstrate you how to include in QuickField model a superconductor. Okay, let's start QuickField now. In QuickField, I create a new problem. Superconductor. Next. Problem type is magnetostatics. Every simulated device is a three-dimensional object, but the model features a rotational symmetry, so the model class is axisymmetric. Length units are millimeters. Finish. On the left is the problem pane, and on the right is the geometry model editor window. In axisymmetric problems, the axis of rotation is a horizontal one, and you should draw only the upper half of the cross-section. First, I'm going to insert a rectangle with dimensions 10 by 21 millimeters, and the insert point will be here. Insert. Then I will insert another rectangle with new insert point located here. Insert. Close. Zoom to fit. Here is the cross section of the permanent magnet, and this is a cross section of the superconductor. In fact, the magnetic field is distributed not only in these two objects, but also in the air outside, so we should draw the air block boundary. Zoom out, switch to Insert Objects mode, draw the line on the axis of rotation, change the line type to half arc, and draw the half arc. Okay. Now let's assign labels. For labels, you can explain the geometric object's meaning and provide physical properties. Switch to Select Objects mode, click to select, and type in the label name here. Air. This is the permanent magnet, and this is the superconductor. I should also assign labels to external boundaries. QuickField automatically assigns proper boundary condition on the axis of rotation, so I have only to assign label to this arc external. Now let's provide physical properties for these labels. Double-click the label name in the tree. Relative permeability of the air is 1. Okay. Relative permeability of the permanent magnet is 1, and the coercive force is 575 kiloamperes per meter. The coercive force direction is 0. This means to the right. Okay. There is no magnetic field inside superconductor, so I can specify 0 magnetic permeability. Okay. Well, in fact, I cannot. Let's specify some small value of magnetic permeability. Okay. Far away from the permanent magnet, magnetic field fades to 0, so at the external boundary I specify 0 magnetic potential. Now, before I can solve the problem, I should build the finite element mesh. Just press this button and the mesh will be generated. Save all problem files and solve the problem. Let's take a look at the results. Let's zoom in. You see, in fact, the magnetic field does not penetrate the superconductor, but the field lines looks broken. That's because of the insufficient mesh quality. Let's solve and refine to get more accurate results. You see, the mesh was automatically adjusted, the problem was simulated. Let's zoom in. Now the field lines looks like smooth curves, which is physically correct. Let's calculate the force. I'm going to use the contour tool. Click to select the permanent magnet, follow to the integrals, and this is the mechanical force. Directed to the right, so the permanent magnet is repelling. The force magnitude is 8.6. Now let's click again to unselect and click to select this superconductor. Mechanical force is 7.6, pointing to the left. The force magnitude differs from the force acting on the permanent magnet. In fact, the integration takes place not only in the body, but along the boundary. And to get accurate results, you should avoid the media boundaries. That is, the correct way to build an integration contour is to draw it in the air some distance away from the body. Don't worry that the contour surrounds some air. There is no magnetic force acting on the air. The contour should be counterclockwise directed. Contour close, mechanical force. I will copy this value, paste it here, and this is force acting on the superconductor. Contour clear, and the same way I'm going to build the contour around the permanent magnet. Some distance away from the permanent magnet, counterclockwise directed. Mechanical force, copy this value, and put it here, permanent magnet. Now you see the difference in magnitude is really small, less than 1%. And what would happen if I change the direction of the coercive force? Let's adjust the field picture and switch on the vectors. Now you see the direction of the coercive force is to the right. What would happen to the force if I change the direction? Open to level properties and change the direction to 180 degrees. Okay. Solve the problem again. Again, let's zoom in. Use the contour tool and build the integration contour. Contour close, integrals, mechanical force, copy this value and put it here. This is the permanent magnet magnetized left, and this is the permanent magnet magnetized to the right. No difference. So no matter which side you turn the permanent magnet to the superconductor will be repelled by the permanent magnet. If you search for the superconductor levitation on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.